For decades, astronomy textbooks described a patient universe. They taught that early galaxies took billions of years to slowly gather their strength, coalescing from primordial gas in a gradual climb toward complexity. This timeline was the foundation of our cosmic history, a steady progression from darkness to light. That assumption was wrong. New data has revealed that the early universe was far more efficient and aggressive than we ever imagined. Galaxies did not merely trickle into existence. They appeared in numbers and sizes that defy the old models. 10 times the galaxies, 10 times the stars, and 10 times the ancient matter were present when the cosmos was still in its infancy. The timeline has shifted, and the early morning of the universe was far brighter than we were told. We are now looking at a reality where massive structures existed while the universe was barely a fraction of its current age. This is not a sudden collapse of science, but a refinement of it. It is the process of a map being redrawn as we finally see the terrain. We once believed we knew the speed limit for how quickly a galaxy could grow, yet we are finding objects that seem to have ignored those limits entirely. The light reaching us now tells a story of an early cosmos that was restless and productive, pushing the boundaries of what we thought was physically possible during the first few 100 million years after the Big Bang. To understand this shift, we must first understand the eye we are using to see it. Floating nearly 1.5 million kilometers away from Earth, at a point of gravitational stability known as L2, sits the James Webb Space Telescope. It does not see the universe the way our eyes do. While we perceive the world in visible light, Webb looks into the infrared, sensing heat signatures and ancient glows that have been stretched across the vacuum of space. This capability is not a luxury, but a necessity. Because the universe is expanding, the light from the most distant objects has been pulled like a piece of elastic, shifting from short, energetic ultraviolet wavelengths into the longer, cooler waves of the infrared spectrum. The telescope is a marvel of precision engineering designed for an environment of absolute cold. At its heart is a primary mirror 6.5 meters wide, composed of 18 hexagonal segments. These segments are not made of glass, but of beryllium, a material that remains stable at cryogenic temperatures. Each segment is coated in a layer of gold, only 100 nanometers thick. This gold coating is critical because it maximizes the reflection of infrared light, ensuring that even the faintest whisper of a signal from the edge of time is captured and directed toward the science instruments. The mirror does not just collect light, it gathers history. Every photon that strikes those golden hexagons has been traveling for billions of years. These particles of light are messengers from an era when the universe was a dense, hot fog of hydrogen and helium. By capturing this infrared glow, Webb allows us to peer through the cosmic dust that obscures our view in visible light. It provides a window into the cosmic dawn, the period when the first stars ignited and began to ionize the surrounding gas, clearing the way for the first galaxies to take shape. The scale of this effort is staggering. To maintain its sensitivity, Webb must be shielded from the heat of the Sun, Earth, and Moon. A massive 5-layer sun shield, each layer thinner than a human hair, protects the mirrors and instruments from thermal interference. This shield creates a temperature gradient so extreme that while one side faces the searing heat of the Sun, the other remains cold enough to freeze nitrogen. In this silent, frozen void, the telescope waits for light that began its journey when the universe was barely 300 million years old. The process of measuring these distant objects relies on a phenomenon known as redshift. As light travels through an expanding universe, the space it occupies actually grows. This expansion stretches the wavelength of the light. A photon that started as a high-energy ultraviolet wave in a young galaxy is stretched by the time it reaches us into a long infrared wave. by measuring exactly how much that light has shifted toward the red end of the spectrum. Astronomers can determine the redshift value, denoted as Z. Redshift is more than just a measurement of color. It is a cosmic clock. A higher redshift means the light has traveled further and for longer, originating from an earlier epoch of time. When we see a galaxy with a redshift of 10 or 15, we are not seeing it as it is today. We are seeing it as it was billions of years ago. This allows us to slice the history of the universe into thin layers, observing how galaxies evolved from small, chaotic clumps of stars into the majestic spirals and ellipticals we see in our local neighborhood. The relationship between redshift and time is a cornerstone of modern cosmology. It tells us that the further back we look, the smaller and younger the universe was. However, the data coming back from Webb is challenging the expected correlation between age and mass. According to previous models, galaxies at very high redshifts should be small, primitive, and sparsely populated with stars. They were expected to be seeds rather than fully formed cities of stars. Yet, we are finding candidates that appear unexpectedly luminous and massive. The mystery lies in the sheer amount of matter required to build these objects so quickly. To create a galaxy with billions of solar masses of stars within a few 100 million years requires an incredible rate of star formation. It suggests that gas was collapsing into stars much more efficiently than our simulations predicted. How did the universe manage to organize such vast quantities of matter in such a short window of time? This is the central tension currently occupying the minds of astrophysicists. The scale of this mystery becomes clearer when we consider the sheer volume of the void. If we imagine the observable universe as a sphere, the early galaxies are not just distant dots. They are markers of a different physical state of existence. The space between us and these objects is not empty, but is filled with the expanding fabric of space-time itself. As this fabric stretches, it carries the light with it, acting as a cosmic conveyor belt that brings the past into our present. The measurement process involves more than just taking a picture. To truly confirm the distance of a galaxy, astronomers use spectroscopy. While an image tells us how bright an object is and what color it appears to be, a spectrum breaks that light apart into its component wavelengths. This allows scientists to identify specific chemical signatures, such as the Lyman break, where hydrogen gas absorbs almost all the light at shorter wavelengths. When this break is shifted deep into the infrared, it provides a definitive spectroscopic confirmation of the galaxy's redshift. This distinction between photometric candidates and spectroscopic confirmation is vital. A photometric estimate is an educated guess based on color filters. It tells us that a galaxy looks like it should be at a certain distance. But spectroscopy is the gold standard. It is the forensic evidence that proves exactly where and when a galaxy existed. The tension in the scientific community often arises during this gap, as early photometric data suggests impossible galaxies, while later spectroscopic analysis works to verify if those masses are real or an illusion caused by other phenomena. When we speak of these galaxies being massive, we are talking about scales that are difficult to comprehend. A galaxy with 10 billion solar masses contains enough material to create 10 billion stars like our own sun. To find such a structure existing only 300 to 500 million years after the Big Bang is like finding a fully constructed skyscraper in a city that was supposed to be nothing more than a collection of tents and dirt paths. The infrastructure required to support such growth, the dark matter halos that pull gas inward through gravity, must have been established with surprising speed. The physical journey of this light is an odyssey across the abyss. A photon leaving a galaxy at redshift 14 has traveled for over 13 billion years. It has passed through voids larger than our entire local supercluster. It has survived the expansion of space and the interference of cosmic dust. By the time it hits the gold-plated mirrors of Webb, it is no longer the ultraviolet light that was emitted by a hot young star. It is a cool infrared signal, a ghost of a dead world. This process reveals the inherent fragility of our certainty. We build models based on the best data available, and those models become the textbooks for the next generation. But the universe is under no obligation to follow our textbooks. The arrival of Webb has shown us that the transition from the Dark Ages, the period before any stars existed, to the era of galaxies was not a slow dawn, but perhaps a sudden awakening. The scale of this shift forces us to reconsider the role of gravity and gas in the early universe. For a galaxy to grow so quickly, it needs an abundant supply of cold gas and a way to convert that gas into stars without blowing it all away via supernova explosions. This balance is delicate. If star formation is too violent, it pushes the remaining gas out of the galaxy, halting growth. The existence of massive early galaxies suggests that there were mechanisms for gas accretion and star formation that we have not yet fully captured in our simulations. As we drift further into this cosmic history, we realize that the instruments we build are extensions of our own curiosity. The L2 point is a lonely place, far from the warmth of Earth, but it provides the silence necessary to hear the universe's oldest secrets. There, the telescope operates as a sentinel, watching for the faintest glimmers of light that have survived since the beginning of time. The measurement of redshift allows us to map the growth of the cosmic web. We can see how matter began to clump together, forming filaments of dark matter that acted as the scaffolding for everything we see today. The galaxies are merely the bright nodes where these filaments intersect. By finding massive galaxies earlier than expected, we are effectively discovering that the scaffolding was erected much faster than we thought. The scale of this exploration is not just about distance in kilometers or light years, but about the compression of time. We are looking at a version of the universe that was significantly smaller and denser. In those early epochs, galaxies were closer together, and the interactions between them were more frequent and violent. The mergers and collisions that shaped the early cosmos happened in a crowded environment, potentially accelerating the growth of massive systems through rapid coalescence. This is where the mystery deepens. If these galaxies grew so quickly, did they also harbor supermassive black holes at their centers? We know that most large galaxies today have a central black hole with millions or billions of times the mass of our Sun. If the galaxies were already massive in the early universe, it stands to reason that their black holes were also growing at an alarming rate. This creates a circular puzzle. Did the black holes help the galaxies form by pulling in gas? Or did the galaxies provide the fuel for the black holes to grow? The data suggests a symbiotic relationship, but one that operates on a timescale that challenges our current understanding of physics. The growth of a black hole is limited by how fast it can consume matter without radiating so much energy that it pushes the remaining food away. To reach billions of solar masses in a few 100 million years requires a rate of consumption that pushes the limits of known theory. The infrared eye of Webb is now showing us that the early universe was not a quiet place of slow assembly. It was a forge. It was an era of extreme density and rapid transformation. Every new spectroscopic confirmation of a high redshift galaxy adds another piece to a puzzle that is larger than we anticipated. We are finding that the impossible is actually happening, and the task of science is now to explain how the impossible became possible. The physical reality of this light is a reminder of our own smallness. We are observing events that took place long before the Earth existed, long before our Sun was born from a cloud of dust, and long before life ever stirred in the depths of an ocean. The light we study today is the only bridge we have to those distant shores. It is a fragile thread of information, stretched by the expansion of the universe, yet it is strong enough to overturn decades of scientific consensus. As we consider the scale of these early structures, we must also consider the void they inhabit. The space between these first galaxies was filled with primordial hydrogen and helium, a neutral gas that blocked most light. This is why the first stars were so important. Their intense ultraviolet radiation stripped electrons from the hydrogen atoms in a process called rionization. This cleared the cosmic fog, making the universe transparent to the light we now detect. Webb's ability to see into the infrared allows it to look through that remaining fog and identify the very objects that caused the reionization. By studying these early galaxies, we are essentially watching the universe wake up. We are seeing the moment when the first lights flickered on in the dark, transforming the cosmos from a cold, opaque sea of gas into the structured, transparent universe we inhabit today. The measurement of this transition is incredibly precise. By comparing the spectra of galaxies at different redshifts, astronomers can track how the state of the hydrogen gas changed over time. They can see the exact moment when the neutral gas became ionized. This allows us to pin down the timing of the cosmic dawn with unprecedented accuracy. Yet, even with this precision, the mass problem remains. The luminosity of these galaxies, how bright they appear, is a proxy for how many stars they contain. When Webb finds a galaxy that is unexpectedly bright at redshift 13 or 14, it suggests a stellar population far larger than any model predicted for that era. It implies that the universe was capable of producing massive amounts of starlight almost immediately after the Big Bang. The scale of this discrepancy is what makes the current research so electric. It is not that the data is wrong, but that the models are incomplete. The beauty of astronomy is that it provides a hard limit on imagination. You cannot invent a galaxy that isn't there, and you cannot ignore one that is. When the telescope delivers a spectrum that confirms a massive galaxy at 300 million years, the theory must change to accommodate the fact. This brings us back to the physical nature of light and time. Because we are looking so far back, we are seeing the universe in its most raw and energetic state. The stars in these early galaxies were likely very different from the stars we see today. They were probably much more massive, burning hotter and dying younger, filling their surroundings with heavy elements that would eventually form planets and people. The gold mirrors of Webb are capturing the first hints of this chemical evolution. By analyzing the light, scientists can look for traces of oxygen or neon, elements that can only be created inside stars. Finding these elements in galaxies at redshift 14 would mean that an entire generation of stars had already lived and died before the universe was even a fraction of a billion years old. The scale of this cycle is breathtaking. In the time it takes for a human to live a single lifetime, a star in the early universe could have been born, exploded as a supernova, and seeded the surrounding space with the building blocks of future worlds. The pace of cosmic evolution was vastly accelerated in those first few 100 million years. We are now entering an era where we no longer have to guess about the beginning. We can observe it. The transition from theoretical models to direct observation is one of the most profound shifts in human history. We are moving from a time of storytelling about the early universe to a time of mapping it. The measurement of these distant objects requires a level of patience and precision that mirrors the journey of the light itself. Astronomers must wait for the telescope to lock onto a target, integrate the signal for dozens of hours, and then carefully peel away the noise of the foreground stars and galaxies to find the one tiny, red smudge that represents a galaxy from the dawn of time. This process is like listening for a single whisper in the middle of a hurricane. The hurricane is the light from every other star and galaxy between us and our target. But through the power of infrared spectroscopy, we can isolate that whisper and translate it into a distance, a mass, and an age. The scale of this achievement is not just technological, but intellectual. It requires us to accept that our understanding of the universe is always provisional. Every time we build a better eye, we find that the universe is stranger than we thought. The impossible galaxies are not a failure of science. They are a triumph of it. They prove that we are capable of asking the right questions and building the tools to answer them. As we drift through these concepts, we can imagine the early universe as a dark ocean, where the first galaxies were like distant lighthouses appearing one by one. For a long time, we thought those lights appeared slowly and faintly. Now we know they flared up with unexpected brilliance, casting long shadows across the cosmic void. The measurement of this brilliance is what leads us to the mass problem. If a galaxy is bright, it usually means it has many stars. But if it has too many stars too early, it breaks our understanding of how gravity pulls gas together. This is the core of the current debate. Are these galaxies truly massive? Or is there something else making them look brighter than they are? One possibility is that the stars in the early universe were simply more efficient at producing light. Perhaps the lack of heavy elements made them burn differently, creating a luminosity that mimics a larger mass. Another possibility is that we are seeing the influence of supermassive black holes, which can emit incredible amounts of energy as they consume gas, adding to the overall brightness of the galaxy. Regardless of the answer, the scale of the discovery remains the same. We have found objects that should not be there according to our old maps. The timeline is being stretched and reshaped. The early universe was a place of rapid growth, intense energy, and surprising complexity. The journey from the L2 point back to Earth is a journey through the history of light. Every photon captured by Webb's gold mirrors has traveled across the expanding void, carrying with it the signature of a time when the laws of physics were forging the first structures of the cosmos. By studying these signals, we are not just learning about distant galaxies. We are learning about the origin of everything. The scale of this perspective is humbling. We are small observers on a small planet, looking back at the very beginning of the story. The fact that we can even perceive these ancient lights is a testament to the laws of physics and our own persistence in seeking the truth. As we continue to analyze the data from JWST and other deep field surveys, we are finding that the early universe was more crowded than we imagined. The number density of these galaxies, how many exist in a given volume of space, is higher than predicted. This suggests that the process of galaxy formation was not a rare event, but a widespread phenomenon that occurred rapidly across the entire horizon of the observable universe. This universality means that what we see in one small patch of the sky is likely representative of the whole cosmos. The impossible galaxies are not anomalies. They are clues to a general rule of cosmic growth that we have yet to fully describe. The early universe was an engine of creation, operating at a speed and scale that dwarfs our previous conceptions. The measurement of this expansion and the resulting redshift remains our most reliable tool. It is the yardstick by which we measure the age of the stars and the distance to the edge of the light. As we refine these measurements, the picture becomes clearer. We see a universe that transitioned from a smooth, hot plasma to a structured web of galaxies with startling efficiency. The physical scale of this transition is almost impossible to visualize. We are talking about billions of light-years of space and hundreds of millions of years of time. Yet, through the lens of the James Webb Space Telescope, these vast distances become manageable data points. The infrared glow becomes a coordinate on a map. This map is still being drawn. Every new image, every new spectrum, adds a line or a point of interest. We are discovering that the cosmic morning was not a slow sunrise, but a sudden burst of light. The galaxies we see at redshift 14 are the first witnesses to this event, standing as sentinels at the edge of time. The scale of their existence challenges us to rethink the relationship between dark matter and visible matter. We know that dark matter provides the gravitational well that allows gas to collect and stars to form. If galaxies grew faster than expected, it may mean that dark matter clumped together more quickly than our models suggested, or that the interaction between dark matter and baryonic gas was more efficient in the early universe. This is the frontier of modern cosmology. We are no longer just observing the universe. We are testing the very foundations of how we think matter behaves on a cosmic scale. The impossible galaxies are the test cases. They are the anomalies that force us to improve our theories, pushing us toward a deeper and more accurate understanding of reality. As we contemplate these ancient structures, we can feel the immense silence of the void they inhabit. These galaxies exist in a version of space that is vastly different from our own, denser, hotter, and far more chaotic. Yet, the light they emitted billions of years ago has traveled through that chaos to reach us in a state of perfect, cold stillness. The measurement of this light is an act of cosmic archaeology. We are digging through layers of time, using infrared wavelengths as our brushes to uncover the ruins of the first stellar cities. Each discovery tells us more about where we came from and how the universe evolved into the place it is today. The scale of this journey is a reminder that the universe always has more to reveal. Just when we think we have solved the timeline, a new instrument opens a new window, and we find that the story is far more complex than we imagined. The transition from the old textbooks to the new data is not a moment of failure, but a moment of growth. We are learning that the early universe was a place of extreme possibilities. It was a time when galaxies could grow to massive proportions in a blink of cosmic time, and where the first black holes could reach sizes that seem impossible by today's standards. This era of rapid evolution set the stage for everything that followed, creating the chemical and structural foundations for future generations of stars and planets. The physical reality of this process is etched into the light we observe. The redshift tells us the distance. The spectrum tells us the composition. The luminosity tells us the scale. Together, they provide a complete picture of an ancient world that defies our intuition but obeys the laws of physics. As we look at these distant, amber-colored glows in the deep field images, we are seeing the very first breaths of the cosmos. We are witnessing the moment when gravity won its battle against expansion on a local scale, pulling matter together to create the first islands of light in an infinite sea of darkness. The measurement of this victory is what allows us to track the history of the universe. From the cosmic microwave background, the afterglow of the Big Bang, to the first stars, and then to these massive early galaxies, we are tracing a line of descent that leads directly to us. We are made of the same elements that were forged in those first violent stellar nurseries. The scale of this connection is profound. The atoms in our bodies were once part of the primordial gas that collapsed into those first galaxies. By looking at JWST Z14-0 and its neighbors, we are essentially looking at our own ancestral home, seen as it was billions of years before our solar system even existed. The infrared eye of Webb has not just found new galaxies. It has given us a new perspective on time itself. It has shown us that the past is not a static record, but a dynamic landscape that we can explore and understand. The shift in our understanding of early galaxy formation is a reflection of our own growth as a species, moving from speculation to observation. The physical distance to these objects is so great that the light we see today left its source when the universe was barely 300 million years old. To put that in perspective, the Earth didn't form for another 9 billion years. We are looking across a gulf of time and space that is almost beyond human comprehension, yet we can measure it with precision. This precision is what allows us to identify the gaps in our knowledge. We can see exactly where the observations deviate from the models. This gap is where the new science happens. It is where astronomers ask why these galaxies are so bright and how they grew so fast. It is where the next generation of theories will be born. The scale of this intellectual journey mirrors the physical journey of the light. It is a slow, steady process of refinement, moving from a broad approximation to a detailed understanding. We are no longer satisfied with roughly or approximately. We want the exact redshift, the precise mass, and the definitive chemical composition. As we drift through the deep fields, we see that the early universe was not a wasteland, but a garden of rapid growth. The massive galaxies found by Webb are like the first giant redwoods of the cosmos, growing tall and strong while everything around them was still small and fragile. They provide a benchmark for what is possible when gravity and gas work in perfect harmony. The measurement of this harmony requires us to look at the universe as a whole system. We cannot understand the galaxies without understanding the dark matter that guides them, or the black holes that power them, or the expanding space that stretches their light. Everything is connected in a vast, interlocking web of cause and effect. The scale of this interconnection is what makes astronomy so rewarding. A discovery about a tiny red dot billions of light years away can change how we think about the physics of gravity here on Earth. It shows us that the laws of nature are universal, operating the same way in the first few 100 million years as they do today. As we continue to peer into the infrared void, we are finding that the universe is more surprising than we ever dared to hope. The impossible galaxies are not problems to be solved. They are invitations to explore. They tell us that there is still so much we don't know, and that the journey of discovery is far from over. The physical reality of these objects, their mass, their brightness, and their age, is a testament to the power of nature to organize itself. From a nearly uniform cloud of gas to massive galaxies with billions of stars in a fraction of a billion years, the universe has shown a capacity for complexity that is staggering. We are now tracing this complexity back to its very roots. By measuring the redshift of the most distant objects, we are pushing the boundaries of the observable universe. We are reaching back toward the moment of creation, using light as our guide and mathematics as our map. The scale of this exploration is a reminder of the beauty of the scientific method. We make a claim, we test it with an instrument, and when the data contradicts the claim, we change the theory. This is how we move forward. This is how we turn the impossible galaxies into a new chapter of cosmic history. As we settle into the silence of deep space, we can imagine those first galaxies as glowing embers in the dark. They are the remnants of a violent and beautiful beginning, their light traveling across the abyss to tell us their story. We are the listeners, the observers, and the inheritors of that ancient light. The measurement of this light is our way of remembering where we came from. It is our way of connecting the present moment to the very first sparks of existence. The scale of this connection is the ultimate journey, a trip across 13 billion years of time and space to find the beginning of everything. The JWST deep fields represent some of the most scrutinized patches of sky in human history. These are not wide panoramic views, but narrow, piercing gazes into a void that appears empty to the naked eye. By staring at these small regions for hundreds of hours, the James Webb Space Telescope accumulates enough photons to reveal objects that have been traveling through the vacuum for nearly the entire age of the universe. In these images, we see galaxies not as spirals or ellipses, but as tiny, distorted smudges of light. These shapes are a result of both their extreme distance and the way gravity from foreground objects bends their light on its journey to our mirrors. The process of identifying these distant candidates begins with photometry. This is the act of measuring the brightness of an object through different filters. Because the universe is expanding, the light from the earliest galaxies has been stretched so far that it no longer exists in the visible spectrum. It has shifted entirely into the infrared. Astronomers look for a specific signature called the Lyman break. This occurs because neutral hydrogen gas in the early universe absorbs almost all ultraviolet light below a certain wavelength. To an observer, the galaxy simply disappears in the shorter wavelength filters and suddenly appears in the longer ones. This dropout technique allows us to flag potential candidates that might be at the edge of the observable universe. However, a photometric candidate is only a hint. It is a suggestion based on color and brightness, but it lacks definitive proof. To move from a candidate to a confirmed discovery, we need spectroscopy. This is where Webb's instruments truly excel. A spectrograph takes the light from a single point and spreads it out into a rainbow of its component wavelengths. By looking for specific absorption or emission lines, the chemical fingerprints of hydrogen and oxygen, astronomers can calculate the redshift with extreme precision. It is the difference between guessing the distance to a mountain by how hazy it looks and using a laser rangefinder to find its exact peak. When this process was applied to the JWST survey, it revealed an object known as JWST 14.2. The spectroscopic measurement placed it at a redshift of 14.32. This number is more than just a coordinate. It is a timestamp. It tells us that the light we are seeing today was emitted when the universe was only about 300 million years old. At that time, the cosmos was in its infancy, a period often called the cosmic dawn. The discovery of JWST 14.2, along with another galaxy identified as JWST 14, at a redshift of approximately 13.90, shifted our understanding of the early timeline. These galaxies were not just present, they were luminous and developed. How did these structures manage to assemble themselves so quickly after the Big Bang? According to previous models, the early universe should have been a place of slow accumulation, where small clumps of gas gradually merged over billions of years to form larger systems. But JWST 14.0 suggests a different story. Its luminosity indicates a significant population of stars already in place, glowing with an intensity that challenges the idea of a slow start. The fact that these galaxies are more common than expected implies that the process of star formation was far more efficient or started much earlier than we had imagined. The light from these objects travels through a universe that is vastly different from the one we inhabit today. In those first 300 million years, the cosmos was smaller and denser. The gas was primarily hydrogen and helium, the raw materials for the first generation of stars. These primordial stars were likely massive and hot, burning through their fuel with an intensity that would dwarf our own sun. Their light began the process of reionization, carving out bubbles of ionized gas in a sea of neutral hydrogen. JWST 14 same exists within this transition, acting as a beacon from a time when the universe was becoming transparent to light for the first time. The luminosity of these early galaxies is a primary source of debate among astrophysicists. When we see a galaxy that appears incredibly bright at redshift 14, the first instinct is to assume it has a massive amount of stellar mass, billions of stars working together to create that glow. If these galaxies truly possess such immense mass so soon after the Big Bang, It creates a tension with our standard models of cosmology. The current framework suggests that dark matter halos, the invisible gravitational wells that pull gas together, take time to grow. For a galaxy to be massive at 300 million years, it would require a dark matter halo that grew with an efficiency and speed that was previously thought impossible. However, brightness is not always a direct proxy for mass. In the cosmic dance of light and shadow, there are other ways to produce intense luminosity without needing billions of stars. One such mechanism is the active galactic nucleus, or AGN. This occurs when a supermassive black hole at the center of a galaxy begins to feed on surrounding gas. As matter spirals into the event horizon, it heats up to millions of degrees, emitting radiation that can outshine all the stars in the galaxy combined. If an early galaxy contains a hungry black hole, its apparent brightness is inflated. The light we see is not coming from a vast city of stars, but from a single violent engine at the core. This realization led to a deeper investigation into the nature of these impossible galaxies. Some initial studies identified candidates with inferred stellar masses exceeding 10 billion solar masses at redshifts between 7 and 9. These numbers were startling, suggesting that some galaxies had reached maturity in a fraction of the time they should have. But as more data flowed from Webb's spectrographs, the picture began to refine. Researchers found that for several of these candidates, the light was indeed coming from an AGN rather than just stars. When the contribution of the black hole is subtracted from the total luminosity, the estimated stellar mass drops significantly. This correction does not erase the mystery. It simply changes its shape. Even after accounting for the influence of active black holes, a discrepancy remains. The data suggests that there are still roughly twice as many massive early galaxies as the standard models predicted. We are left with a universe that is more productive than our simulations allowed. The puzzle has shifted from how can these possibly exist to why did they form so much faster than we thought. This indicates that while the fundamental laws of cosmology, the expansion of space, and the role of dark matter remain intact, our understanding of baryonic physics, how normal matter behaves and collapses into stars, is incomplete. The efficiency of star formation in the early universe may have been fundamentally different from what we observe today. In the modern era, star formation is a regulated process. When stars are born and die as supernovae, they blow gas out of the galaxy, slowing down the birth of new stars. This feedback loop acts as a cosmic thermostat. But in the dense, high-pressure environment of the early universe, this mechanism might have operated differently. The gas may have collapsed more violently and rapidly, allowing galaxies to build up their stellar populations in short, intense bursts. This brings us to the concept of the little red dots. These are a distinct population of compact reddish objects discovered by Webb that do not fit neatly into our existing categories. They are small, but they are incredibly bright in the infrared. The debate over their nature is ongoing. Some astronomers believe they are extremely dense galaxies composed entirely of old stars, while others argue they are primarily supermassive black holes accreting matter at an incredible rate. It is possible that they are a combination of both, small stellar cores orbiting monstrous black holes. These little red dots represent another layer of the cosmic puzzle. If they are indeed black holes, their existence at such early times raises a separate, equally pressing question. How did the black holes get so big so fast? A black hole starting from the collapse of a single star would take billions of years to reach millions or billions of solar masses through steady accretion. To see them in the first few 100 million years suggests that they may have started as seeds, perhaps the direct collapse of massive gas clouds, bypassing the stellar stage entirely. As we look at these objects, we are seeing a universe that was far more active and chaotic than the serene void we imagine today. The early cosmos was a laboratory of extremes. Gravity was fighting against the rapid expansion of space, while radiation from the first stars fought to clear the fog of neutral hydrogen. In this environment, galaxies like JWST, Z14, and the little red dots were the pioneers. They were the first structures to organize themselves out of the primordial soup, setting the stage for everything that would follow. The tension between Webb's observations and previous models is a healthy part of the scientific process. It does not mean that our understanding of the Big Bang is wrong, but it does mean that our maps of the intervening time need to be redrawn. The standard model of cosmology, known as lambda CDM, provides the skeleton of the universe, the dark matter and dark energy that dictate its overall expansion and structure. But the meat on those bones, the gas, the stars, and the black holes, is governed by complex astrophysics that we are still learning to simulate. The discrepancy in galaxy numbers tells us that our simulations were perhaps too conservative. We assumed a certain speed for gas cooling and a certain rate for star formation based on what we see in the local universe. But the early universe was not the local universe. It was denser, hotter, and lacked the heavy elements, carbon, oxygen, iron, that help gas cool and collapse today. The first stars had to form from pure hydrogen and helium, which requires different physical conditions. By observing these distant galaxies, we are discovering the actual rules of engagement for the cosmic dawn. We must remember that every measurement in astronomy is an interpretation of light. When we say a galaxy has a certain mass, we are using a model to translate luminosity into kilograms of stars. If the model changes, if we discover that early stars were brighter or more blue than modern stars, the calculated mass changes too. This is why spectroscopy is so vital. It allows us to move beyond brightness and look at the actual chemistry of the galaxy. When we see the signature of oxygen in a galaxy only 300 million years after the start of time, it tells us that at least one generation of stars had already lived and died, forging those heavy elements in their cores and seeding the interstellar medium. This cycle of birth and death happened with incredible speed. The timeline from the Big Bang to the first oxygen-rich galaxies is a blink of an eye on a cosmic scale. It suggests a universe that was eager to evolve, pushing toward complexity as quickly as the laws of physics allowed. The massive galaxies Webb has found are not anomalies in the sense of being mistakes. They are evidence of a more dynamic early history. They show us that the capacity for structure to emerge from chaos is greater than we had credited. The scale of this discovery is mirrored in the technology used to find it. To see these objects, Webb must remain incredibly cold, shielded from the heat of the sun and the Earth by a tennis court-sized sun shield. It sits nearly 1 million miles away at the L2 point, where it can stare into the deep dark without interference. The gold coating on its mirrors is not for aesthetics. It is specifically designed to reflect infrared light with maximum efficiency. Every single photon that hits those hexagonal segments has traveled for 13 billion years, crossing an expanding void, bending around gravitational lenses, and surviving the journey through intergalactic dust, just to tell us about the state of the universe at redshift 14. When we analyze a galaxy like JWST Z17-0, we are not just seeing a distant object, we are seeing a survivor. We are seeing a structure that managed to coalesce and shine during a period of immense instability. The fact that these galaxies were more numerous than expected means that the seeds of the universe, the initial fluctuations in density from the Big Bang, were perhaps more effective at triggering collapse than our models predicted. This leads us to consider the role of dark matter halos again. We cannot see dark matter, But we know it is there because its gravity holds galaxies together. In the early universe, these halos acted as the scaffolding for everything else. If Webb is finding more massive galaxies, it may mean that the scaffolding was built faster, or that the gas fell into those scaffolds with greater efficiency. This refinement of the model does not break cosmology. It completes it. It fills in the gap between the smooth, uniform glow of the cosmic microwave background and the complex, structured universe we see around us today. The cosmic microwave background shows us a universe that is almost perfectly smooth, just 380,000 years after the Big Bang. There are no galaxies then, only tiny ripples in density. The journey from those ripples to the massive, luminous galaxies of JWST Z14 is the story of the first few 100 million years. By filling this gap with actual observations, Webb is turning a theoretical timeline into a visual history. We are moving from a period of "we think this happened" to "we can see that this happened." As we drift further into these deep fields, the patterns begin to emerge. The early universe was not a place of lonely islands, but perhaps a network of rapidly growing hubs. These massive galaxies were the centers of activity, drawing in gas and merging with smaller neighbors at a frantic pace. This era of growth was the foundation for everything. The stars born in these first galaxies provided the heavy elements that would eventually form planets, moons, and eventually life. The physical reality of this process is humbling. We are observing events that happened so long ago that the light we see has been stretched by the expansion of space itself. The ultraviolet light emitted by those first stars is now infrared, a ghostly echo of its former self. But in that echo, there is enough information to rewrite our textbooks. We are learning that the universe was not shy about its beginnings. It did not wait billions of years to become interesting. It began with a flourish, creating massive structures and supermassive black holes almost as soon as it was physically possible. This realization changes how we view our own place in time. We often think of the early universe as a distant alien realm, but it is actually our origin story. Every atom of carbon in our DNA and every grain of iron in our blood was once forged in a star. Some of those stars may have been part of the very galaxies Webb is finding now. By measuring the redshift and luminosity of JWST Z14, we are tracing the lineage of matter back to its first meaningful organization. The silence of the deep field images is deceptive. While they look like still life paintings, they represent a period of unimaginable violence and energy. The birth of these galaxies involved colossal collisions of gas clouds, the eruption of supernovae, and the relentless pull of black holes. All of this activity was happening across the entire horizon of the observable universe, creating a tapestry of light that we are only now beginning to unravel. As we continue to analyze the data, the impossible nature of these galaxies fades, replaced by a new set of questions. We no longer ask if they can exist, but how they were sustained. We ask how they managed to keep their gas from being blown away by their own intense radiation. We ask how many more of them are hiding in the darkness, waiting for a longer exposure or a deeper look. The transition from shock to inquiry is where science lives. It is the process of turning an anomaly into a law. The scale of this intellectual shift is profound. For decades, we had a comfortable narrative of cosmic evolution, a slow, steady climb toward complexity. Webb has shown us that the climb was more like a leap. The early universe was a place of rapid acceleration, where the first structures appeared with a speed and scale that defied our expectations. This does not mean the standard model is broken. It means the model is being refined by reality. We are now in an era of precision cosmology. We are no longer guessing at the age of the first galaxies based on vague light signatures. We have the spectra. We have the redshifts. We have the evidence of oxygen and carbon. The universe is speaking to us in a language of wavelengths, and for the first time, we have an instrument sensitive enough to hear it clearly. The massive early galaxies are the first words of that conversation, telling us that the beginning was far more spectacular than we ever imagined. As we contemplate these distant amber glows, we can feel the sheer scale of the void they inhabit. They exist in a version of space that has since expanded by a factor of many times over. The distance between them and us is not just a measure of miles, but a measure of evolution. Between the light leaving JWST 14 and its arrival at Webb's mirror, entire galaxies rose and fell. Stars were born and died in trillions, and our own solar system coalesced from a cloud of dust. The measurement of this journey is what allows us to sleep with a sense of wonder. We know that the universe is vast, but we also know that it is intelligible. The fact that we can build a machine, send it 1,000,000 miles into the cold, and use it to decode the light of 300-million-year-old galaxies is a testament to the power of curiosity. We are small observers in an infinite sea, but our ability to understand the laws that govern that sea gives us a connection to the furthest reaches of time. The early universe remains a frontier, but it is a frontier that is becoming familiar. With every new data release from JWST and other surveys, the impossible becomes the observed. We are mapping the cosmic dawn, one photon at a time, uncovering a history of rapid growth and unexpected brilliance. The galaxies we once thought couldn't exist are now our guides, leading us deeper into the mystery of how everything began. The brightness of these early galaxies is a seductive piece of evidence, but in astronomy, luminosity can be a mask. When we see a point of light that appears too bright for its age, our first instinct is to assume it represents a massive collection of stars. We imagine billions of suns packed into a compact space, creating a gravitational well so deep that it challenges our understanding of how quickly matter could gather. However, brightness does not automatically equal stellar mass. There are other ways for a galaxy to shine with an intensity that mimics the glow of 1,000,000,000,000 stars. One such mechanism is the active galactic nucleus, or AGN. At the heart of many early galaxies, a supermassive black hole may have been feeding on vast reservoirs of primordial gas. As this matter spirals inward, it heats up to millions of degrees, releasing a torrent of radiation that can outshine every star in the galaxy combined. For a time, this led some researchers to believe they had found impossible galaxies, structures far too massive for their era. The room went very quiet during some of these early data reviews, as teams realized the light they were seeing might not be coming from stars at all, but from the violent appetite of a central black hole. When astronomers began to correct for this AGN contribution, the numbers shifted. Some of those initial mass estimates, which had suggested galaxies far larger than anything the models allowed, were revised downward. The impossible peaks became more manageable. Yet, even after these corrections, a persistent puzzle remained. While some of the most extreme cases were explained away by black hole activity, the overall count of massive early galaxies still sat roughly twice as high as the previous models predicted. The problem had not vanished. It had simply become more precise. This leaves us with a refined mystery. Why was the early universe so efficient at producing these structures? If we accept that some of these galaxies are truly massive, we have to look at the physics of star formation itself. In the modern universe, stars form in a relatively measured way. Gas clouds collapse, fragment, and ignite over millions of years, with the resulting radiation often blowing away the remaining gas and slowing down further growth. This is known as feedback, a cosmic braking system that prevents galaxies from growing too quickly. But in the first few 100 million years, this braking system may have worked differently. The primordial gas, mostly hydrogen and helium, was denser and hotter. It is possible that star formation in these early hubs was far more efficient, converting gas into stars at a rate we rarely see today. We are forced to ask how such an intense burst of creation could be sustained without the galaxy essentially blowing itself apart. This suggests that the relationship between gas, gravity, and radiation in the cosmic dawn was fundamentally different from the laws we observe in our own galactic neighborhood. This efficiency points toward a deeper interaction with the dark matter halos that provided the initial scaffolding. These invisible spheres of gravity acted as the primary attractors, pulling in vast streams of cold gas from the intergalactic medium. If these halos were more massive or more numerous than previously thought, they would have created larger catchment areas for matter to accumulate. The galaxies we see now are the luminous evidence of those hidden dark matter structures. We cannot photograph a halo, but we can see its signature in the way stars cluster and how the light is distributed across the deep field. The growth of these early black holes adds another layer of complexity. For a black hole to reach millions or billions of solar masses by redshift 14, it must have grown at an astonishing rate. This raises a classic chicken and egg problem in cosmology. Did the massive galaxies form first and feed the black holes, or did the black holes act as seeds that accelerated the gathering of galaxies? The data from Webb suggests a symbiotic relationship, where the growth of the central engine and the surrounding stellar population were locked in a frantic race toward maturity. Amidst this search for mass and scale, another strange population has emerged: the little red dots. These are compact, intensely red objects that appear in the deep infrared images. Their color is a clue to their nature, suggesting either an immense amount of dust obscuring their light or an extreme redshift that pushes their emission further into the infrared spectrum. The scientific community remains divided on what these dots actually are. Some believe they are tiny, ultra-dense galaxies packed with stars. Others argue they are primarily accreting black holes shrouded in cosmic dust. The debate over the little red dots highlights a recurring theme in the work of the James Webb Space Telescope: the transition from photometric candidates to spectroscopic truth. A photometric candidate is essentially an educated guess based on the color of a pixel. It tells us where a galaxy likely is and how bright it seems. But spectroscopy is different. By breaking the light into its constituent wavelengths, astronomers can find the exact drop-off point where hydrogen gas absorbs light, providing a definitive redshift. When we move from a guess to a measurement, the universe often reveals a more nuanced story. The discovery of JWST Z14T0 and other high redshift objects has shown that while some galaxies are indeed massive, they are not breaking the laws of physics. They are simply pushing them to the limit. This distinction is vital. It means that we do not need to discard our entire understanding of the Big Bang or the nature of dark energy. Instead, we are refining the baryonic physics, the rules governing how normal matter behaves, within a stable cosmological framework. This refinement process is where the most exciting science happens. It is the slow, methodical work of adjusting variables in a simulation until the virtual universe matches the observed one. When researchers find that their models underpredict the number of early galaxies by a factor of 2, they don't throw away the model. They look for the missing mechanism. Perhaps the gas cooled faster than expected. Perhaps the first stars were significantly more massive than today's stars, producing more light per unit of mass. The implication is that the cosmic dawn was not a uniform event, but a patchwork of extremes. In some regions of space, matter collapsed rapidly, creating these luminous hubs of activity. In other regions, the universe remained dark and empty for much longer. This variance suggests a level of cosmic heterogeneity that we are only beginning to map. The early universe was a landscape of high-contrast peaks and valleys, where the first islands of light fought against an overwhelming ocean of darkness. As we consider these structures, we must remember that they are not static. The massive galaxies Webb sees at redshift 14 are the ancestors of the galaxies we see today. They merged, collided, and evolved over 13 billion years. The frantic star formation and the ravenous black holes of the early era eventually settled into the more stable spiral and elliptical shapes that populate our modern sky. We are looking at the chaotic adolescence of the cosmos, a time of rapid growth and violent transformation. The presence of these galaxies so early in time forces us to reconsider the timeline of chemical enrichment. For oxygen and carbon to exist 300 million years after the beginning, the first stars must have lived and died with incredible speed. These population 3 stars, the very first generation, were likely monsters of mass, burning through their fuel in a few million years before exploding as supernovae. They were the cosmic alchemists, turning simple hydrogen into the complex elements that would one day form rocky planets. The scale of this process is almost impossible to visualize. We are talking about trillions of stars igniting across a horizon that was still shrinking and expanding simultaneously. The energy released by these first explosions would have rionized the universe, stripping electrons from neutral hydrogen atoms and making the cosmos transparent to light for the first time. This epoch of reionization is the curtain that Webb is finally pulling back, allowing us to see the actors on the stage. Every photon captured by the 6.5-meter mirror is a piece of this puzzle. When we analyze the spectrum of a distant galaxy and find a signature of ionized helium or oxygen, we are witnessing the aftermath of those first stellar deaths. We are seeing the moment when the universe ceased to be a simple cloud of gas and became a complex machine capable of creating chemistry. The massive galaxies found by Webb are the primary engines of this transformation, the places where the most intense alchemy occurred. The tension between the observed data and the old models is not a sign of failure, but a sign of progress. In science, a crisis in the data is actually an opportunity for a breakthrough. By finding more galaxies than expected, Webb has given astronomers a specific target to hit. It has told them exactly where the current models are lacking. The work now shifts from discovery to explanation, as theorists attempt to build new simulations that can account for this early abundance of light. This process reminds us that our understanding of the universe is always an approximation. We build a map based on the best data we have, and then we build a better telescope to find where the map is wrong. The impossible galaxies are simply markers on the map where the terrain is more complex than we imagined. They invite us to look closer, to question our assumptions about how gas collapses under gravity, and to wonder what other surprises are hidden in the deep infrared. As we drift through these thoughts, the image of those distant, amber-hued galaxies remains. They are small points of light in a vast void, yet they hold the secrets of everything that followed. Their existence proves that the universe was ready for complexity, almost from the start. The journey from the smooth glow of the cosmic microwave background to these structured cities of stars happened with a speed that defies our intuition, but follows a logic we are slowly decoding. The silence of the deep space images belies the energy of the events they depict. We see a still image, but we are actually looking at a scene of colossal collisions and stellar eruptions. The light has traveled for billions of years to reach us, crossing distances that dwarf our entire solar system by factors of millions. This light is a bridge across time, connecting our modern world to a version of the cosmos that no longer exists. The massive galaxies are not just astronomical objects. They are milestones. They mark the transition from the dark ages to the age of light. By studying them, we are tracing the very first steps of the cosmic journey. We are learning that the early universe was a place of ambition, where matter did not merely drift, but surged together to create the first beacons in the dark. The realization that these galaxies were more common than predicted suggests that the seeds of structure, the quantum fluctuations from the Big Bang, were remarkably efficient. These tiny ripples in density were amplified by gravity into massive wells of matter far faster than we had credited. It is a reminder that, on a cosmic scale, the smallest beginnings can lead to the most gargantuan results. As we continue to process the data from JWST and other deep-field surveys, the picture becomes clearer. We are seeing a universe that was eager to grow. The early galaxies were not anomalies. They were the vanguard of cosmic evolution. They paved the way for everything that followed, creating the heavy elements and the gravitational structures that would eventually allow stars like our Sun to form in the quiet suburbs of a mature galaxy. The intellectual journey accompanying these discoveries is as vast as the physical one. We have moved from the certainty of textbooks to the uncertainty of new data, and finally toward a more sophisticated understanding of reality. This cycle of doubt and discovery is the heartbeat of astronomy. It ensures that we never stop looking, never stop questioning, and never assume that we have seen everything there is to see. The amber glow of JWST Z14 remains a symbol of this era. It is a tiny smudge of light on a digital sensor, but it represents a fundamental shift in our cosmic origin story. It tells us that the universe was bright, active, and structured much earlier than we ever dared to hope. The impossible has become the observed, and in doing so, it has expanded the boundaries of our imagination. The underlying architecture of these early galaxies is not something Webb can see directly as a physical map, but it is something astronomers can infer through the behavior of gravity. To understand why so many massive galaxies appeared so quickly, we have to look at the invisible scaffolding of the cosmos. Dark matter halos. In the standard cosmological model, dark matter provided the gravitational wells that pulled in primordial hydrogen and helium. These halos acted as cosmic cradles, creating regions of high density where gas could cool, collapse, and ignite into stars. The presence of massive galaxies just 300 million years after the Big Bang suggests that these dark matter halos grew with a surprising efficiency. It implies that the early universe was not a smooth, featureless soup, but a landscape already etched with deep gravitational trenches. While we cannot photograph dark matter, its influence is written in the distribution and luminosity of the galaxies Webb detects. If the halos were larger or formed more rapidly than previously simulated, the impossible nature of these galaxies vanishes. They are no longer anomalies. They are simply the natural result of a more aggressive gravitational beginning. This realization allows us to separate two different layers of scientific understanding. On one hand, we have the global cosmology, the overall expansion and geometry of the universe defined by lambda CDM. On the other hand, we have baryonic physics, the messy, complex rules governing how gas and stars actually behave inside those dark matter wells. Most of the current tension does not come from a failure of the global cosmology, but from an incomplete understanding of the baryonic physics. We are learning that our simulations of star formation were perhaps too conservative. We assumed that feedback mechanisms, such as the energy released by supernovae or the radiation from black holes, would blow gas out of these early galaxies and slow their growth. But the data suggests that in some corners of the early universe, gravity won more decisively than we expected. The gas stayed, the stars ignited, and the galaxies grew at an accelerated pace. This shift in perspective transforms the narrative from one of cosmic crisis to one of refined detail. We are not rewriting the history of the Big Bang. We are simply correcting the timeline of how quickly matter organized itself. This process of refinement forces us to acknowledge the limits of our current evidence. When we see a bright point of light at redshift 14, we are seeing a snapshot in time, but we are missing the context of its surroundings. We do not yet know if these massive early galaxies were isolated giants or if they existed in dense clusters that acted as the first metropolitan hubs of the universe. The luminosity we measure is a proxy for mass, but it is an imperfect one. A galaxy can appear bright because it has trillions of old stars, or it can appear bright because it has a few million incredibly massive hot stars that burn with a blinding intensity before dying young. Distinguishing between these two scenarios requires spectroscopy of unprecedented precision. Every time Webb delivers a new set of spectra, the astronomers are essentially checking the ID of the galaxy to see if its brightness is coming from stellar mass or from an active galactic nucleus, a supermassive black hole devouring matter at the center. When an AGN is discovered, it often shrinks the estimated mass of the galaxy, bringing it back into alignment with our models. Yet, even after these corrections, a surplus remains. There are still more massive galaxies in the early universe than our best simulations predicted. This persistent gap is where the real mystery resides. It suggests that there is a fundamental piece of the puzzle missing. Perhaps a new understanding of how dark matter interacts with gas, or a different way that the first stars were born. The implications of this extend beyond just the size of galaxies. They touch upon the very nature of time and causality in the early cosmos. If structure formed this rapidly, it means the universe reached a state of complexity much faster than we ever imagined. The transition from a hot, dense plasma to a structured web of galaxies was not a slow crawl, but a sprint. This raises questions about the seeds of these structures. These seeds were planted during inflation, the trillionth of a second after the beginning, as quantum fluctuations were stretched to galactic scales. If we find that the early universe was more lumpy than expected, it may tell us something profound about those first moments of existence. It means the initial conditions of our universe were tuned in a way that favored rapid collapse and early brilliance. We are essentially using these distant galaxies as probes to study the physics of the Planck era, using the largest structures in the sky to understand the smallest possible scales of reality. As we drift further into this realization, we must accept that some questions may remain unanswered for a long time. The nature of the little red dots and the exact mass of JWST 140 are data points in a much larger conversation about how the universe breathes. We are observing a process of cosmic maturation. The early universe was a place of extreme volatility, where the rules were being tested in real time. The radiation fields were more intense, the gas was purer, and the gravitational collapses were more violent. In this environment, the standard laws of star formation we observe in the Milky Way may not have applied. We might be looking at a lost era of stellar evolution, where stars grew to hundreds of times the mass of our Sun, living fast and dying hard, leaving behind a chemical legacy that we are only now beginning to decode. These first-generation stars were the bridge between the simplicity of hydrogen and the complexity of everything we see today. Without their rapid growth and explosive deaths, the heavy elements required for planets and life would not have existed in sufficient quantities. The impossible galaxies were therefore necessary. They were the factories that forged the building blocks of our existence. The silence of these deep field images is deceptive. Behind every golden smudge of light is a storm of activity. gas clouds colliding at thousands of kilometers per second, black holes spinning with unimaginable energy, and stars igniting in bursts of ultraviolet radiation. We are witnessing the birth pangs of the cosmos. The fact that we can see this at all is a testament to the precision of human engineering. To capture these photons, we had to build a mirror capable of detecting temperatures just above absolute zero, placed 1,000,000 miles away from the heat of the Earth. We have extended our sight back to the very edge of the observable, and in doing so, we have found that the universe is more ambitious than our theories allowed. This tension between observation and theory is not an error. It is the engine of science. When the data contradicts the model, it means the model is about to grow. We are currently in that window of growth, where the old certainty of a slow-forming universe is being replaced by a more dynamic, rapid-fire version of cosmic history. This shift does not diminish the majesty of the cosmos. It enhances it. It reveals a universe that was eager to create light, eager to build structure, and eager to evolve. The massive galaxies found by Webb are reminders that we are part of a lineage of complexity that started almost immediately after the dawn of time. We are the distant descendants of those first luminous hubs, carrying within our own atoms the ash of stars that burned 13 billion years ago in galaxies that shouldn't have existed. As we contemplate these ancient structures, we realize that the universe is not a finished product, but an ongoing experiment. The laws of physics provide the boundaries, but the actual history, the timing, the scale, and the distribution of matter is where the story unfolds. Webb has shown us that the story began with a flourish. The early universe was not a quiet awakening, but a sudden explosion of complexity. The massive galaxies were the first milestones on this road, proving that gravity is a patient but relentless force, capable of sculpting empires of stars in a fraction of the time we once thought possible. We are now mapping the geography of this ancient era, identifying the peaks and valleys of the first cosmic landscape. Each new galaxy found at high redshift is another piece of evidence that the universe possesses a capacity for rapid organization that still surprises us. The limits of our current knowledge are not walls, but horizons. Every time we reach the edge of what the models can explain, we find a new phenomenon waiting to be categorized. The impossible galaxies have become the new baseline. They have shifted the goalposts of astronomy, forcing a generation of physicists to rethink how gas cools and how black holes grow. This is the true legacy of the James Webb Space Telescope. It does not provide final answers, but instead provides better questions. It takes the settled science of textbooks and turns it back into a living, breathing mystery. We are learning that the universe is far more efficient at creating beauty and complexity than we ever gave it credit for. The amber light of the first galaxies is a signal across time, telling us that the journey from nothingness to everything happened with an intensity and speed that defies intuition. It is a reminder that in the vastness of space and time, the only constant is change, and the only certainty is that there is always more to discover. The process of revising our cosmic timeline is a quiet, iterative dance between evidence and imagination. We move from the shock of an impossible observation to the steady work of mathematical refinement. The massive galaxies Webb has uncovered do not stand as monuments to a broken science, but as markers for a more nuanced understanding of how nature operates under pressure. We are discovering that the early universe was a place of extreme efficiency, where the conversion of primordial gas into stars happened with a vigor that our previous simulations simply missed. This realization brings a strange comfort. It suggests that the drive toward complexity is a fundamental feature of existence, an inherent momentum that began almost as soon as the laws of physics were established. As we look at these distant points of light, we are seeing the universe in its infancy. Yet it was already displaying a sophistication that mirrors our own galactic neighborhood. The transition from the cosmic microwave background, that first faint glow of a baby universe, to the structured brilliance of JWST Z10 represents one of the most profound leaps in history. We are bridging the gap between a featureless sea of plasma and the intricate architecture of a billion galaxies. This bridge is built from infrared photons, traveling across an expanding void for 13 billion years, just to land on a gold-coated mirror at L2. The scale of this achievement is often lost in the technical data. We have effectively built a time machine that allows us to witness the era when the first light pierced the cosmic dark. This period, known as the cosmic dawn, was the moment the universe woke up. The massive galaxies we find there are the first lanterns, lighting the way for everything that would follow. They provided the heavy elements and the gravitational anchors that allowed smaller systems to coalesce. Every star in our own night sky is a descendant of those early, violent bursts of creation. The tension between our models and these observations reminds us that science is not a collection of static facts, but a living process of correction. We accept the current data not as a final truth, but as the most accurate map we have for now. The impossible galaxies are only impossible if we assume our previous maps were complete. Once we allow the models to grow, the impossibility vanishes, replaced by a deeper curiosity about the mechanisms of gravity and gas. We are learning to be comfortable with the unknown, recognizing that the gaps in our knowledge are where the most exciting discoveries are hidden. Slowly, the focus shifts from the furthest reaches of the infrared spectrum back toward the familiar. The light we have been tracing across billions of light years eventually settles into the steady rhythms of the modern cosmos. We move away from the high redshift frontiers, passing through the era of peak star formation, and drifting back through the slow maturation of the Milky Way. The universe has cooled, expanded, and grown quiet in many of its vast stretches, leaving behind a tapestry of galaxies that now drift in a state of graceful equilibrium. The journey from the edge of time brings us closer to home. We leave the cold vacuum of L2 and the hexagonal gold mirrors behind, descending through the thin veil of our own atmosphere. The cosmic scale begins to shrink, returning from millions of light years to the familiar dimensions of a single solar system. We pass the outer reaches of the Kuiper Belt, moving inward past the gas giants and the asteroid belts, until we find ourselves orbiting a steady yellow sun. The vastness we have explored does not make our own world feel small. It makes it feel precious. To be a conscious observer in a universe that spent billions of years organizing itself into a place where consciousness could exist is a rare and quiet miracle. We are the way the cosmos contemplates its own origin. The same atoms that once burned in those massive early galaxies now reside in our lungs, our blood, and the cells of our brain. We are made of the very light that Webb is searching for. The noise of the world fades away as we settle into the stillness of the present moment. The cosmic wind dies down, and the rush of expanding space slows to a heartbeat. There is no more need for telescopes or equations here. There is only the weight of your body against the bed, the rhythm of your breath, and the safety of the room around you. The universe is vast, but you are held within it, a small and secure part of a much larger whole. The stars continue their slow rotation above us, indifferent to our questions, but constant in their presence. They have watched the galaxies grow from sparks into empires, and they will watch as we drift into the quiet hours of the night. The mysteries of the early universe can wait until the morning. For now, there is only the darkness, which is not a void, but a blanket. It is a soft, enveloping silence that stretches from your window to the furthest reaches of the cosmic dawn. The light of JWST 140 has finally reached its destination. Its long journey is over. The photons have been captured, the data has been read, and the story has been told. Now, it is time for the mind to let go of the scale of billions and return to the scale of seconds. The expansion of space slows to a stop in your thoughts. The redshift fades into a deep, calming blue. The cosmic clock winds down. The ancient light grows dim. The distance collapses into a single point of peace. The gravity of sleep pulls gently. The mind drifts like a lonely star. The silence is absolute. The void is warm. The journey is complete. The universe is at rest. Sleep well tonight.